Welcome to topic number 9, making a brick fly, or our introduction to aerospace propulsion. Over the next 4 videos, we're going to talk about the basics of propulsion, piston propeller aircraft, jet and gas turbine engines, rockets, and then have an entire video on efficiency of our propulsion systems, how we estimate efficiency, and how we can compare efficiency between different propulsion system types. So just stay tuned and we'll get started with video 1, where we talk about an introduction and piston propeller. And as usual, we start with our cartoon. Well, scratch number 24. He did pretty good, though, right up to the jet engine test. And now a little video of a 787 engine blade out test. In this test, we see what happens when we detonate, separate a blade from the fan, and the result on the engine. Obviously, this is a bit of an aside over what we're going to discuss over the next several videos, but it's a good starting point. So for the next 4 videos, I want you to ask and try to answer the following questions. How do we generate thrust? Could we just throw passengers overboard? I mean, it might not be a very good idea, but would it work? Could we do it to generate thrust? Ask, what are the basic types of propulsion system? And we'll talk about those in each of the next 3 videos. And then how do we measure efficiency, which we'll spend most of the 4th video on. What are the different measures of efficiency and how do they compare to each other? And then ultimately, across all of these videos, I want you to think about what are the differences and similarities between aeronautical propulsion systems and astronautical propulsion systems. Just like when we were talking about the anatomy of an aerospace craft, there were some similarities you wouldn't have expected and some differences you might not have expected. You will see that here in these cases. So, how is thrust produced? Well, in general, we produce thrust by changing the momentum of air or mass going in versus coming out. We have a side closed control volume with open ends. Obviously, in a rocket, this open-ended here is a reservoir of all of our propellants. But the big difference is we take a mass flow in at a given velocity, and we have a mass flow out at a given velocity. Those mass flows may or may not be the same. Some may be close to each other, some may be strictly identical, and some may be totally different. But it's that change in momentum. As a result, we get a resulting force on our thrust device, and a resulting force on the fluid. It's Newton's third law in action. The same thing that applies for generating lift and drag applies for generating thrust. So how do we estimate the momentum change? For a simple control volume where we just have an actuator that produces work, i.e. something like a propeller or a fan and a turbofan, we have a mass flow in, the same mass flow out, and we just have a delta in velocities. And therefore we can calculate thrust, which is the time rate of change of momentum, as the mass flow times the change in velocity. And m dot is in something like kilograms or slugs per second. And it's very easy. So m dot v infinity is the mass flow in, m dot vj is the mass flow and momentum out. Simple. Now, to do that, we accelerate the fluid. So that gives us a change in kinetic energy. And unlike mass flow, which is just related to velocity, kinetic energy is obviously related to velocity squared. So our delta in kinetic energy is, of course, 1/2 the mass flow times the quantity Vj squared minus V infinity squared. Now, for a rocket, what do you think V infinity is? For a jet engine, what do you think V infinity is? But they're all similar and the same. But as you can see, our thrust goes up linearly with velocity. Our kinetic energy goes up with the square of velocity difference. So that's going to lead us to something when we get to efficiencies in the future. So keep that in mind. Okay, so we just did that little bit of evidence, a little bit of things. I want you to think about this. In general, for our thrust devices or propelling systems, we trade thrust versus efficiency, but really it's specific thrust versus efficiency, because efficiency is how much thrust you can produce for energy input, and specific thrust is how much thrust you can produce for a given mass of propulsion system or mass flow rate of fluid. The lower our specific thrust, the higher our efficiency. So rockets have huge specific thrust, very poor efficiency, while propellers and reciprocating engines may have very low specific thrust, but quite high efficiency. We're going to discuss a lot more of this in video 4, but just keep this in mind as we go through the next several slides. Okay, so that brings us to the end of our quick introduction. The rest of this video we're going to spend on propellers and piston props. And this sets the groundwork for all of the turbojet and turbofan work we'll do in video 2. So how does a reciprocating engine work? Well, this is an example of a 4-stroke OTTO cycle engine. And the reason I say it's an Otto cycle engine is you can see we have a spark here. If it was a diesel cycle, it would be purely compression ignition. And what I mean by 4-stroke is that we produce power on only one of 4 strokes. So we have an intake where the piston descends, pulling in fuel and air. We have the compression where the piston ascends, followed by an ignition. And then we have a power stroke where the gas is expanding, giving us power, and then we exhaust it. There's also a 2-stroke engine where we get power out of one out of every 2 strokes on the engine. They're slightly different, but the same principle applies. We trade efficiencies in operation of the engine for efficiencies and usefulness in the total number of cylinders. It's a bit of a trade. We can have both 4 and 2-stroke engines in our propulsion systems on aircraft, but 4-stroke are more common. We do that to generate what's called shaft power. So our reciprocating engine generates shaft power that turns a propeller. Now, depending on the type of engine, there may be a gearbox, but let's just think of a propeller that is physically attached directly to the crankshaft of the engine. That propeller then turns in the fluid. It imparts work on the fluid, imparts momentum to the fluid, and then we get thrust. So we get power out of our engine and shaft power, and then power available in our flow, PA. And those are not the same. In fact, PA will strictly be less than, but can be theoretically equal to P. And that difference is called a propeller efficiency. So this is the first efficiency we're talking about. It's the efficiency of our propeller to create thrust power from shaft power. And again, eta PR is going to be less than or equal to 1. And in all real cases, less than 1. Just so you know, propeller efficiency is the function of advance ratio. So how does a propeller work? It captures a stream of air molecules in what we call a stream tube, and it does work on the particles and adds energy. And it does that by behaving as a mini wing. It changes the momentum and direction of the flow. Particles approach that air approaches the propeller at a low velocity. It imparts a higher velocity and therefore more energy. This change in momentum gives us our thrust. One of the things to know about propellers is because they are open, they are not in a shroud, that the tips are the same as a wing. We have to have 0 pressure difference between our tip here and our tip here, and small differences, otherwise we get crosswise flow. That means propellers can only impart a small pressure change on our flow, otherwise they cease to work. And they therefore can only generate so much thrust per size area, something we can do a lot more if we, say, enclose our system like a turbojet or a turbofan engine. Okay, that brings us to the end of our propeller discussion and piston propulsion system discussion. Now, we talked briefly about advance ratio. In there, we didn't give you any more information. If you look at the supplemental materials at the end of the lecture notes and in Anderson, they'll tell you a little bit more about advance ratio, but we're not going to dwell on that. You just need to know the propeller efficiency is a function of advance ratio. In video 2, we're going to go into jet propulsion, turbojets, ramjets, turbofans, and the like. And that's a little bit more involved because we see a lot more of that in aerospace today than we see piston props. So I hope to see you soon in video number 2.